All right, today we're going on a bit of an adventure along the number line. Now I know, it sounds simple, but this is a landscape you see every single day. And trust me, it's hiding a universe of secrets right under your nose. I mean, really think about it. You use numbers all the time, right? To count stuff, measure things. But have you ever just stopped and wondered what's hiding between the number 1 and the number 2? Or even between, say, zero point 0.5 and zero point 0.6? Well, as we're about to find out, there's a whole universe packed into those tiny spaces, just waiting for us to explore. Okay, so let's get this expedition started. And I want you to forget the boring ruler from math class. Instead, picture this number line as a path, a road that stretches out infinitely in both directions. Our mission is to walk this path and discover every single type of number that exists. Of course, every good explorer needs a place to keep what they find. So for our journey, we're going to have this virtual bag. As we walk the line, we'll collect every kind of number we come across. The goal? By the end, we'll have a complete set. You ready? Let's go. Our walk starts now.
All right, so as we start walking away from 0, heading in the positive direction, the first numbers we see are, well, they're the ones you'd expect, the most familiar ones. These are the easy ones to just grab and toss right into our bag. And the very first things we spot, they're called the natural numbers. You'll see them with the symbol N. These are literally the first numbers you ever learned as a kid, right? 1, 2, 3, and they just keep on going forever. So let's scoop them all up and pop them in the bag. And wow, an infinite collection right off the bat. Not bad.
But hang on a second. Let's look back at where we started. We totally missed a super important one, 0. We got to add that to the bag. Now, by taking all those natural numbers and adding 0 to the mix, we've just created a brand new set. These are the whole numbers, or W for short.
Okay, but we know this line doesn't just go in one direction, right? If we look behind 0, there's a whole other world of numbers, the negative ones. So let's grab all of them, -1, -2, -3, you get the idea, and toss them in the bag. Our collection is looking pretty good now. We've got all the positive whole numbers, all the negative ones, and 0 sitting right in the middle. This whole group is called the integers, and its symbol is Z, which actually comes from the German word zahlen, which just means to count.
So our bag is starting to feel pretty heavy with all these integers. We've got these nice, neat points marked out at -2, -1, 0, 1, 2, and on and on. But what about all that space between those points? I mean, if we were to zoom way in, say between 0 and 1, it might look like just empty space. But it's not empty at all. It's absolutely packed with numbers, like 1/2 or 3/4. All those fractions you use for recipes or for measuring things, they all live right here. So yeah, our work is definitely not done yet.
All right, let's get back to collecting. Let's scoop up all of these fractional numbers and get them into our bag. This new collection is way, way bigger, and it's called the rational numbers. The symbol for this set is Q, which makes sense because it comes from the word quotient, and a fraction is really just the result of a division, right? The key thing to remember here is this. Any number that you can possibly write as one integer over another, as long as the bottom one isn't 0, is a rational number. And that actually includes all the integers we already collected, because a number like 5, for example, can just be written as 5/1.
So it's one thing to say, oh yeah, there are numbers between 1 and 2, but how do you actually find them? Like in a systematic way. Let's say we need to find exactly 5 of them. Well, there's actually a brilliant little trick for this. And here's how you do it. It's a pretty cool trick. Since we're looking for 5 numbers, we're going to use the denominator 5 plus 1, which is 6. Simple enough. So we just rewrite 1 as 6/6, and we rewrite 2 as 12/6. And just like that, boom, the numbers in between just reveal themselves. 7/6, 8/6, 9/6, and so on. It's a super neat, foolproof method every time. Okay, let's take a quick inventory. We've collected the natural numbers, the whole numbers, the integers, and now this massive infinite collection of fractions, the rational numbers. It really feels like we must have every single point on the number line covered now, doesn't it? I mean, think about it. Between any 2 rational numbers you can possibly name, we can always find another one. It seems like the line is just totally, completely full. Our bag has got to be overflowing by now, and our journey is complete. Or is it? And here comes the plot twist. It turns out, even with every single fraction imaginable stuffed into our bag, the number line is still full of holes. And not just a few, infinitely many of them. The numbers that live in these gaps, they're a completely different species. And this discovery, back in the day, was absolutely shocking. We're talking around 400 BC. The followers of the famous Greek mathematician Pythagoras, the Pythagoreans, they found these numbers that just could not be written as a simple fraction. And the legend is kind of dark. It says that the guy who discovered it, Hippocrates, was actually drowned for revealing this secret. Why? Because it completely shattered their belief that the entire universe could be explained with nice, neat, whole numbers and their ratios.
So, what are these mysterious numbers? They're called irrational numbers. The name says it all. They can't be written as a ratio of integers. You've definitely heard of some of them. Think of the square root of 2 or the super famous pi. You could almost call them the rebels of the number line.
So how can you actually spot one of these in the wild? Well, the secret is all in its decimal form. A rational number's decimal is always predictable. It either stops, like 0.5, or it repeats a pattern forever, like 0.333 and on and on. But in a rational number's decimal, it's pure chaos. It goes on forever with no repeating pattern whatsoever. And that fundamental difference is what sets them completely apart. Okay, now that we know about these strange, wild, irrational numbers, it's time to finally complete our collection. Let's get them all. We'll scoop up every last one of these irrational numbers and add them to our bag. And by combining all the rational numbers with all the irrational numbers, our bag is finally, truly full. This complete collection, the whole shebang, is called the real numbers. You'll see it with the symbol R. Now, at long last, every single point on that number line has a number to call its own. Our journey down the line is finally complete. But you might be wondering, how can we even be sure these irrational numbers are actually there? Are they just concepts? Well, no, we can prove it. Let's take the square root of 2. We can pinpoint its exact location. Here's how. Just draw a simple square with sides that are 1 unit long. Thanks to the Pythagoras theorem, we know the diagonal of that square is exactly the square root of 2. Okay, now take that square and place one corner at 0 on the number line. Then just swing that diagonal down like it's the arm of a compass. The point where it lands on the line, that is the exact location of the square root of 2. See, it's not just some abstract idea, it's a real physical point on the line. So, there you have it. We've journeyed down the number line, we've filled our bag with every type of real number that exists. We've seen how they all fit together, like puzzle pieces, to create that complete, continuous line we use all the time. But you know what? The exploration never really ends. And now, it's your turn. So, I'm going to leave you with a final puzzle to think about. We know for sure that the square root of 2 is irrational. Same with the square root of 3. But what about the square root of 4 or the square root of 5? How about the square root of 9? Here's the question. Are the square roots of all positive integers irrational? I want you to really think about it and see if you can find an exception that breaks the rule. Hey, thanks so much for joining me on this adventure down the number line.